In this lecture, I will discuss an important topic in classical mechanics, and that is central force problem. I will also give you an idea of qualitative description of various possible orbits for a particle moving under the influence of central force. Now, what is the meaning of central force? In order to define a central force, first we need a center of force. Okay, so consider a coordinate system like this. You have three axes x, y and z, and the origin is treated as the center of force. Suppose there is a particle of mass m at this point, and this point has spherical polar coordinates r, theta and phi, where r is the radial distance, theta is the polar angle and phi is the azimuthal angle. Okay. Now, if the force acting on this particle satisfies two conditions, the first one is if force depends only on r, not on theta and phi. The force acting on this particle will be same if you vary theta or if you vary phi. It will change only if you vary radial distance. That is the meaning of this first statement. Okay, the force acting on this particle m depends only on the radial distance. Okay, it is independent of theta and phi. The second condition is F is directed towards or away from the origin. The force acting on this particle will always be along the direction of r cap or opposite to r cap. If these two conditions are satisfied, then we can say that the force acting on this particle is a central force. And mathematically, we can write it as vector F is equal to F of r cap. That is, the magnitude will depend only on the radial distance and the direction will be either along r cap or opposite to r cap. This F of r can be positive or negative. If this F of r is positive, this force will be directed away from the force center. And if F of r is negative, this force will be directed towards the force center, like this yellow arrow. Okay, so this is the definition of central force. So in order to define a central force, we need a center of force. Here we consider this origin as center of force. Then for a particular particle of mass m situated at a point whose coordinates are r, theta and phi, the force should satisfy these two conditions. Okay, so we can say that there is or it is a spherically symmetric one. That is, if this particle is placed on the surface of a sphere with center as the center of force, then the magnitude of force will be same. Irrespective of this angle theta and phi, the force acting on this particle will be the same. The force will change only if this distance varies. Okay. Now, what are the properties or consequences of that definition? The first one is torque about center of force is 0. Okay, for a particle moving under the influence of a central force, the torque acting on the particle about center of force is 0. Because torque is defined as the cross product of r and f, where r is the position vector of the particle. And in this case, F is F of r cap. So this becomes F of r into this vector r, we can write it as r cap, and this F of r and r are scalar. We can take that outside. R cross cap r cross, that will be 0. So torque about force center is 0. That term is very important. Torque is defined with respect to some reference point. Torque about center of force is 0 in the case of particle moving under the influence of a central force. The second point is if the torque about force center is 0, then angular momentum about force center will be a conserved quantity. Because according to Newton's second law, torque is rate of change of angular momentum. And the important point is this is a vector equation. So dl by dt equal to 0 means L is a constant. That is, the magnitude of L is constant and direction of L is also constant. Okay, this is a vector L is a constant. So magnitude as well as direction will be a constant. And the third point is the plane of trajectory will always, or this is actually the trajectory. The trajectory will always confined to a plane. The trajectory will always confined to a plane. Why? Because we have the equation for angular momentum L, that is R cross P. We already mentioned that L is a constant, that is the direction of L is also a constant, and the direction of cross product is perpendicular to both the vectors. So the direction of L is perpendicular to the direction of R and the direction of P. Suppose you have a particle like this. This is center of force and this is the position vector R. Suppose this is the momentum vector P. Then R cross P will be directed away from the plane of the board. R cross P, the cross product, the direction will be perpendicular to the plane of the board and it is directed away from the plane of the board. Okay. Suppose this body moves out of plane. Okay. Suppose if this body moves out of plane, then what happens? This R will not be in this plane of the board. Okay. R will not be in the plane of the board and that will be out of plane. Okay, R is the position vector of the particle. If the particle is not in the plane of board, R will not be in the plane of board. Then L is always perpendicular to R and P. In this case, if the particle is right here, L is perpendicular to this board. If the particle goes anywhere in this board, the angular momentum will be out of plane. But if this particle moves out of plane, then the angular momentum will change direction. And for a particle moving under the influence of central force, that is not possible. L will be a constant. So the particle will always confined to the same plane. Okay, so that is the third consequence of particle moving under the influence of central force. The trajectory will always confined to a plane. Okay, now we will discuss about the equation of motion. We already mentioned that the motion is in a two-dimensional plane. So we can use either Cartesian coordinates xy or polar coordinates r theta to write the Lagrangian. For central force, we have this definition. F is F of r cap and the potential is minus integral F of r dr, because force is minus dv by dr. So V is minus F of r dr. Since F of r, this is a function of r only, this integral will give you a function which is a function of only this radial coordinate r. Okay. And that radial coordinate is actually, in terms of Cartesian coordinates, it is square root of x square plus y square. So V will be a function of r, or we can say that V is a function of x and y. Okay. Now, when we write Lagrangian, we can either use Cartesian coordinates or plane polar coordinates, because the motion is in a plane. So we have Cartesian coordinates or plane polar coordinates. In terms of Cartesian coordinates, the Lagrangian is half m into velocity is square root of x dot square plus y dot square in Cartesian coordinates. So half m v square becomes half m x dot square plus y dot square. And Lagrangian is T minus V, kinetic energy minus potential energy. And potential energy V is a function of x square plus y square, root of x square plus y square. So this is a Lagrangian in Cartesian coordinates. And we can say that this Lagrangian depends on x, y, x dot and y dot. And if you write the Lagrangian in plane polar coordinates, that becomes L is equal to half m r dot square plus r square theta dot square. This much term represents the kinetic energy. Kinetic energy, the velocity contains radial velocity and angular velocity. And total V is square root of r dot square plus r square theta dot square. Therefore, kinetic energy becomes half m r dot square plus r square theta dot square. Minus potential energy is V of r. So, L can be written as the function of r, r dot and theta dot. We can see that theta is missing in this Lagrangian. And a coordinate that is absent in the Lagrangian is known as cyclic coordinate. So, when we write the Lagrangian in Cartesian coordinates, all the coordinates are present in the Lagrangian and there is no cyclic coordinate. But when you write the Lagrangian in plane polar coordinate, theta is absent in the Lagrangian, so there is one cyclic coordinate. And if you have a cyclic coordinate in the problem, then the solution of the problem is very easy. So we will choose plane polar coordinate in order to write the Lagrangian of a central force problem. Okay. So what is Lagrangian of central force problem? L is equal to half m r dot square plus r square theta dot square minus V of r. First we will write the equation of motion in theta. It is dou L by dou theta minus d by dt of dou L by dou theta dot equal to 0. This is Lagrange's equation. In this case, dou L by dou theta is 0 because theta is absent in the Lagrangian. So dou L by dou theta, the partial derivative of L with respect to theta is 0. Dou L by dou theta dot, partial derivative of this L with respect to theta dot is mr square theta dot. Substituting here, you will get minus d by dt of mr square theta dot equal to 0. You can multiply with a negative sign. You will get d by dt of mr square theta dot is equal to 0. This is actually a second order ordinary differential equation. And on integration, okay, this is a process of integration. This d by dt will go and you will get mr square theta dot is equal to constant. Okay, if you differentiate this expression, you will get this one. Okay, so one integration will give you a constant of motion. One integration will give you a constant of motion. And mr square theta dot is nothing but the constant magnitude of angular momentum. We already mentioned that in the case of central force problem, the magnitude of angular momentum will be a constant, and this mr square theta dot is nothing but the magnitude of angular momentum. Okay, and that is a constant. And this is known as first integral of motion. This is known as first integral of motion because this L is the result of integration of a second order differential equation. Okay, Lagrange's equation is a second order ordinary differential equation. One integration will give you a constant, and that is known as first integral of motion, and that is the constant magnitude of angular momentum. So we have one equation, mr square theta dot equal to L. Now we will write equation of motion in R. Dou L by dou R minus d by dt of dou L by dou R dot equal to 0. Dou L by dou R is mr theta dot square minus dou V by dou R. Dou L by dou R dot is mr dot. Substitute these values back in this expression. You will get mr theta dot square minus dou V by dou R minus d by dt of mr dot equal to 0, or d by dt of mr dot equal to minus dou V by dou R plus mr theta dot square. So, not easy to do one integration. In the earlier case, it is easy to do one integration because the right hand side is 0. But here the right hand side contains R and it is a function of t. There is also theta dot. It is also a function of t. So it is not easy to integrate this one. But we have L is equal to mr square theta dot. So that will give theta dot equal to L by mr square. So substitute for this theta dot. Then you will get d by dt of mr dot equal to minus dou V by dou R plus L square by mr cube. Substitute for this theta dot. You will get this term. Okay. Now I can write it as d by dt of mr dot equal to minus dou by dou r of v of r plus L square by 2mr square. Why? Because when you take the partial derivative of this term minus L square by 2mr square, that is this last term minus L square by 2mr square. When you take the partial derivative with respect to r, L square by 2m is a constant, minus 1 by r square, derivative is 2 by r cube. So this 2 and this 2 will cancel and that term becomes L square by mr cube, and that is exactly here. Okay, L square by mr cube. So you can write the right hand side as minus dou by dou r of some function of r, some function of r. Okay, now multiply both sides with r dot. So the left hand side is r dot into d by dt of mr dot, and r dot is nothing but dr by dt. So right hand side you multiply with the dr by dt, both are same. Okay, this left hand side is nothing but d by dt of half m r dot square, d by dt of half m r dot square, because half m into r dot square derivative is 2 r dot into dr dot by dt. 2 will cancel and the rest is here. Okay, so the left hand side is simply d by dt of half m r dot square. Right hand side you can write it as a total differential minus d by dt of v of r plus L square by 2mr square. Because suppose you have a function f which is a function of r, but that r is a function of t. Okay, f has no explicit dependence on t. F is a function of r and r depends on t. Then what is the procedure for taking total derivative of f with respect to t? df by dt is, first you have to take the partial derivative of f with respect to r, then take the derivative of r with respect to t. That is exactly done here. Dou by dou r of a quantity which is function of r, then into dr by dt. So this is exactly minus d by dt of that quantity. So you can take this term to the left hand side. So it becomes d by dt of half mr dot square plus L square by 2mr square plus v of r equal to 0. Now you can do the integration. So integrating, you will get half mr dot square plus L square by 2mr square plus v of r is equal to constant. Again, after one integration, you got one constant. So this is another first integral of motion, and on inspection we can see that that is nothing but total energy, because this half mr dot square is radial kinetic energy. L square by 2mr square. What is L square by 2mr square? We can substitute back the value of L. L is from this expression, L is mr square theta dot. So we can substitute for this L. M square r raised to 4 theta dot square, L square becomes m square r raised to 4 theta dot square divided by 2mr square, and that is half m r square theta dot square. Half m r square theta dot square is actually angular kinetic energy, and this term plus the first term will give you total kinetic energy. So total kinetic energy plus potential energy, that is nothing but total energy of the particle. So for central force problem, there are two first integrals of motion. One is magnitude of angular momentum, the second one is total energy. And in this example, it is very clear that what is the advantage of cyclic coordinate. If a coordinate is cyclic coordinate, then the first integration is very easy and you will get one constant of motion easily. But in the second case, since r is not cyclic, it is very difficult to arrive at this expression. Okay, it is very difficult to arrive at this expression for first integral of motion. Okay, so that is the advantage of a cyclic coordinate. Now, what is the solution of the problem? We have two equations. After one integration of differential equation in theta, we will get f mr square theta dot equal to L, and after one integration of a differential equation in r, we will get half m r dot square plus L square by 2mr square plus v of r equal to E. So both these equations are first order ODE, because already one integration is done and we got two integration constants. One is angular momentum, the other one is total energy. From this expression I can write d theta by dt equal to L by mr square. So this is a first order differential equation. From this expression I can write dr by dt equal to square root 2 by m e minus v of r minus L square by 2mr square. Simply take these terms to the right hand side and multiply with the 2, divide with n, take the square root. Okay, that is r dot. R dot is nothing but dr by dt. So these two are first order differential equation. In order to solve completely, you have to do one more integration. So d theta by dt, integrating, or you can write it as L by m r of t whole square. This r is actually a function of t. Okay, now you can take this dt to this side, and integrating you will get theta as a function of time. Theta as a function of time. Solving this differential equation by taking these quantities to the left hand side and dt to the right hand side and integrating, you will get r as a function of t. Okay, and you can substitute this r of t here in order to find theta as a function of t. So that is the final solution of the problem. You can find the polar coordinate r and theta at any instant of time t in terms of the angular momentum, total energy, and the integration constants comes from here. Actually, the integration constants from these integrations will be the initial value of theta naught and initial value of r. Okay, so if you know the initial theta naught and r naught and total energy as well as angular momentum, you can find the position of particle at any instant of time. This is the procedure for solution of central force problem. Now I will discuss an important topic, reduction of a two-dimensional problem into one-dimensional problem. We already know that a central force problem is a two-dimensional problem. There are two variables r and theta, and we have this first integral of motion L is equal to mr square theta dot, and using this expression we can write theta dot as L by mr square. And the second first integral of motion, that is total energy, it is half m r dot square plus r square theta dot square plus v of r. We know that this first term is actually kinetic energy. It contains radial kinetic energy as well as angular kinetic energy, and this last term is potential energy. And this expression for energy contains both r and theta. We can replace this theta using this first expression, theta dot equal to L by mr square. Substituting that value, you will get E equal to half m r dot square plus L square by 2 mr square plus V of r. So this expression now contains only one variable r. Okay, only one variable r and its time derivative. Okay, so suppose your motion was in an elliptical trajectory, and suppose it is a planetary motion. Suppose it is sun and a planet is moving around the sun in an elliptical orbit. Its radial coordinate r is this one and its polar angle is this one, theta. And the variation of r with the time, r dot, is in this direction, and the angular velocity r theta dot is in this direction. The resultant of these two will give you the actual velocity of the particle at any instant of time t. Now consider this case, that is a particle is attached to the end of a string and the other end of the string is in your hand, and you rotate this particle in a circle. Okay, you rotate this particle in a circle. The particle is attached to a string, the other end of the string is in your hand. Okay, the particle is now moving in a circle, in a horizontal circle, with the axis as vertical. Suppose you switch on a light from this side and you are observing the shadow of this stone or this particle on a wall. Okay, so you are standing here, you are rotating a particle in a circular path, in a horizontal circle, and you switch on a light source here, and you can see the shadow of that motion in this plane, and that motion will be in a straight line. When this particle moves from here to here, that shadow will move from here to here, and when this particle come back to this point, that shadow will come back to this point. And when particle moves in this direction, shadow will move in this direction. Particle when come back to this initial position, shadow will come back to this position. So this two-dimensional motion, that is motion in a circle, when you project, you can see that it is motion in a straight line. So the two coordinates r and theta reduces to the single coordinate r. And exactly the same you can do here. If you visualize this two-dimensional motion as an equivalent one-dimensional problem, you can say that the sun is right here. The particle will go up to this point and it will come back to this point and then go to this side and come back to this side. So that is equivalent to particle moving from here to here and come back to this point and go to this point and come back to here. Okay. So this motion in an ellipse is equivalent to a one-dimensional problem like this. Sun is here and the particle will go to this point. This is the maximum distance and then go to this distance. This is the minimum distance from Sun. Okay. So this is the reduction of a two-dimensional problem into one-dimensional problem. I hope it is clear. Now, if the particle has only one coordinate r, then velocity will be simply r dot. Okay, if in the case of a particle moving in one dimension, if there is only one coordinate changing, then the velocity will definitely the time derivative of that coordinate. So velocity is simply r dot. And the kinetic energy will be simply half m r dot square. Okay, so when you reduce this problem to an equivalent one-dimensional problem, the first term itself will give you the total kinetic energy. Then this second term you can consider with along with this potential energy, and these two terms combined together, you can define effective potential. You can define effective potential. What is the meaning of effective potential? Okay, why it is known as effective potential? You know that the total energy actually contains two terms, the kinetic energy and potential energy. And kinetic energy itself has two parts. One is radial kinetic energy half m r dot square. Second one is angular kinetic energy half m r square theta dot square. When you substitute for this theta dot in order to reduce this two-dimensional problem to one-dimensional problem, the second term becomes L square by 2m r square. And now this is in a single coordinate. When it is in a single coordinate, the kinetic energy will be simply half m r dot square. And you have to incorporate this term along with the potential energy. Okay, because it is not possible to write it along with the kinetic energy. You have only one coordinate changing, that is r. And the time derivative of that quantity will give you velocity r dot. And half m v square will give you kinetic energy. So this term itself defines the entire kinetic energy of the particle if it is the motion in a single coordinate or if it is the variation of a single coordinate. Then the rest of terms, that is L square by 2m r square plus the actual potential of the problem, should be interpreted as a potential energy, and that is known as effective potential. That is known as effective potential. So the total energy E can be written as half m r dot square plus V effective, where V effective is the actual potential plus this term L square by 2m r square. So this term is very important. For any central force problem, the effective potential is actual potential plus L square by 2m r square. Okay, now we will move on to the classification of orbits, and the key idea is from this expression. Total energy equal to half m r dot square plus V effective. This implies E minus V effective, that is equal to half m r dot square, and half m and r dot square, all these quantities are positive, so it should be greater than 0. Or we can say that if E is less than V effective, that means this term becomes negative. This term is negative means the r dot velocity is imaginary. Okay, that is no allowed motion for energy, total energy less than V effective. Okay, first we will consider the case of Kepler problem. The potential for central force problem will be a function of r only, and if it is of the form V of r equal to minus gmm by r, where gmm is constant, so we can write it as minus k by r. If potential energy has this form, then it is known as Kepler potential, and the problem is known as Kepler problem. Then V effective becomes V effective is defined as L square by 2m r square plus the actual potential energy of the problem. Here the actual potential energy is minus k by r. So V effective is L square by 2m r square minus k by r. Okay. Now this is a plot of distance on the x-axis, distance from force center. This origin is actually force center and the x-axis is distance from force center to the particle. Y-axis is actually energy. It can be potential energy or it can be total energy. So the y-axis has quantity having dimension of energy. And here I plotted 3 graphs. This green one is the plot of minus k by r by taking k value as 1. Okay, by taking k value equal to 1. That is, this is a plot of minus 1 by r. This is a plot of minus 1 by r. So for r is equal to 1, you will get this value as minus 1. Okay. So this is the actual potential for a k value 1. Now this blue curve, this is L square by 2m r square. It is L square by 2m r square by taking L is equal to half and m is equal to 1.25. That will make L square by 2m r square. If I take L as half, m as 1.25, this is nothing but 1 by 10 r square. 1 by 10 r square. Okay, where r is the distance marked on this x-axis. Okay, so I took these numerical values and I plotted minus k by r and L square by 2m r square. Now this yellow curve is actually the sum of these two. That is L square by 2m r square minus k by r. That is V effective. This yellow curve is V effective. So this green one is actual potential energy minus k by r. This blue one is L square by 2m r square and this yellow one is the sum of the two and that is V effective. Okay. Now we will discuss 4 different cases for different total energy. Here already we fixed the angular momentum, and for any central force problem angular momentum and total energy will be conserved quantity. So here we fixed L. Now we want to fix total energy. Depending on the value of total energy, the trajectory will change. So first we will consider the case of a positive energy. Okay, that is this red one, and it is nothing but total energy equal to 1. Total energy equal to 1. So a particle with a total positive energy, and you can see that at this distance from the force center, here you have the force center, and at this distance, this total energy, this red line is above this yellow line, above this yellow curve. So the condition E greater than V effective is satisfied. Okay, E should be greater than V effective in order to make it a positive quantity. So for this distance, E minus V effective is positive, so that is an allowed motion. So the particle will come close to the force center because this is an attractive potential. So for any particle of mass m, this force center will attract that. So the particle will come closer and closer to the force center. Now as the particle moves towards force center, all these regions are physically possible because total energy line, this red line, is above the yellow line. But after this point, okay, when you reach at this point, this total energy and V effective becomes equal. What does it mean? If E equal to V effective, then that R dot becomes 0. And if you go beyond this, okay, if you move closer to force center beyond this point, then that means V effective is greater than total energy. And this quantity becomes negative. Okay, so it is not allowed. So it is not allowed. There is no physically possible motion for V effective greater than total energy. That means the particle can come close to the force center up to this distance, then it has to go back. Okay, this is the minimum distance, or it is known as distance of closest approach. So we will consider the real situation. This is the center of force. This black dot is the center of force, and a particle is coming from, say, infinity, and it is having a non-zero angular momentum, means its velocity vector will not be along the line of r. Okay, this r is the position vector with respect to position vector of this particle with respect to force center. If velocity is in this direction, then r cross v will be 0, that is angular momentum will be 0. But here we are considering a case of non-zero angular momentum, so the initial velocity vector will be not in the same direction as that of r. So it will be like this, and this particle come closer and closer to the force center, and this is the minimum distance, or this is the distance of closest approach. Particle can never go beyond this, and then it will go back to infinity. So again the distance r increases. Okay, so r initially decreases up to this distance. This is distance of closest approach, and then it go back to infinity. Okay, so this point at which r dot equal to 0, the entire velocity is tangential. Here you can see that at this point the velocity, you can have the radial component and the theta component. Okay, but at this point there is no radial velocity. All the velocity is tangential. Okay, for all other points the velocity have one component along the radial direction or along the r coordinate, but at this point there is no component in this r direction. Okay, entire velocity is tangential, so r dot is 0, and this point is known as turning point. Okay, the point at which r dot equal to 0 is known as turning point, and in this graph this intersecting point is the turning point. Okay, so the particle will go back to infinity from that point. So the motion is not bounded. Particle will come from infinity and then go back to infinity. There is no upper bound. There is an inner bound. Particle can never go beyond this point, but there is no upper bound. Okay, there is no upper bound. I think it is clear. Now you consider the case with the total energy equal to 0. That is this green line. Again, you can see that all the cases that we mentioned in the case of E greater than 0 is applicable here also. Because for this distance, this green line is above the yellow line, that is E is greater than V effective. Here also E is greater than V effective. Here also E is greater than V effective. Up to this point, E is greater than V effective. So no issues. But beyond this point, E is less than V effective. So that is not physically possible. So particle will go back to infinity. Particle will come from infinity nearer to the force center up to this point, then go back to infinity. So the path will be something like this, the earlier one. Okay, but if we do it quantitatively, we can show that the first one will be a hyperbola and the second one will be a parabola. Again, there is no upper bound, there is only a lower bound. Particle can only come up to this distance. This distance is known as distance of closest approach. Okay. Now you consider the third case, energy E less than 0. Energy E less than 0. That is, in this graph, you have this black line. Okay. So here you can see that beyond this distance R2 and below this distance R1, this yellow line is above the black line. Between R1 and R2, this yellow line is below the black line. For physically possible motions, V effective should be less than total energy. So the only allowed distances are between R1 and R2. So there are two bounds. There is an upper bound. Particle can never go beyond R2 and particle can never go beyond R1. Okay, below R1 and above R2 are forbidden regions. The allowed regions are above R1 and below R2. So the trajectory, one possibility is an ellipse like this. This is the minimum distance R1 and this is the maximum distance R2. All the other distances are between these two values. But this is not the only possibility. We can consider a case like this. You can consider two circles, one with radii R1, the other with radii R2. And the particle motion is bounded between these two radii. Means particle can say start from here and go like this, like this, like this, like this. It need not be closed. It is bounded, but it is not closed. Okay, closed means you have to end at right here. Okay, if you end up on the point where you started, then you can say that it is a closed orbit. But here it is not a closed orbit, but it is a bounded orbit. Bounded orbit. There is a lower bound as well as an upper bound. So from this graph, we can say we can have only this information. Motion is bounded between two distances R1 and R2. Now we will consider the last case. Total energy is equal to V effective minimum. Here we can see that there is a minimum for effective potential, and if your total energy is exactly equal to that minimum value, what happens? It is clear that if you go beyond this distance, then the yellow line will be above the blue line. That is, total energy is less than V effective, and below this R value also, this total energy is less than V effective. It is not physically possible for the particle to change the value of R. The only possible R is this distance. Okay, here R dot will be 0 and no motion possible beyond this or below this radius. Okay, so we can say that the particle will move in a circle. The only possible distance is R, and where R dot is 0, entire velocity is tangential, so the motion will be in a circle. Motion will be in a circle. Okay, so this is the classification of orbits based on different values of energy. Okay, now in a single figure we can represent these motions like this, and here we are assuming that the motions are hyperbola, parabola, ellipse and circle. This is the force center. This is the force center. For E greater than 0, the path will be a hyperbola and the distance of closest approach is minimum. Okay, this distance RH is the least one. You can see in this graph, this is the least distance. In the case of E equal to 0, the distance is slightly greater than this one. In the case of this red line cuts this yellow line at this point, but this green line cuts this yellow line at a slightly higher value of R. At a slightly higher value of R. So for parabola, you can draw like this. This green one, this is with E equal to 0, and the distance from force center is slightly higher compared to the hyperbolic orbit. And the third one is with E less than 0, and there are two bounds, R1 and R2, and the R1 value will be greater than RP, and that is also clear from this graph. Okay, this point and this point, if you compare these points, you can see that this one is greater compared to this first point. Okay, now the last one is a circular orbit, and that R value is still greater compared to the previous three cases. So these are the R values. The first one is the intersecting point of red and yellow. Second one is intersecting point of green and yellow. Third one is intersecting point of black and yellow. Fourth one is this point. Okay, so this distance increasing. So this is the possible trajectories in the case of a Kepler problem. I hope it is clear. Now I want to add two more points to this. The first one is, what happens if V of r is equal to plus k by r? That is a repulsive potential. Minus k by r is an attractive potential. If you have a scattering problem, then here you will have a nuclei and an alpha particle will come from infinity towards the force center. Then what happens to the trajectory? It will be something like this. Okay, it will be something like this. But for the potential minus k by r, the trajectory will go around the force center. Okay, here also you have a distance of closest approach. Here also you have a distance of closest approach. In the first case, the particle will go like this, and in the second case, the particle will move around the force center. Why? If you look at the velocity vectors, here you can see that this is the initial velocity. After some time, this is the velocity. If you take the change, this is initial velocity direction, this is final velocity direction. If you take the change delta v, that will be something like this. So the acceleration will be in the direction of delta v, and it is away from the force center. It is away from the force center. That is, force is away from force center. This is a repulsive force. So the force should be directed away from the force center. But in the second case, it is minus k by r. The force should be directed towards force center. So if you draw like this, if the particle move around the force center, then the velocity vector is, initial velocity vector is like this, final vector is like this. So the change delta v is pointing towards force center. So acceleration is towards force center, that is, force is towards force center. So in the case of an attracting potential, the trajectory will be go around the force center, and in the case of a repulsive potential like scattering cases, it will be, the trajectory will be like this. Okay. Now, the second point I want to mention is the same nature of orbits. The nature of orbits we discussed so far is open. Open means the first two cases, hyperbola and parabola. Okay. They are open orbits. And then the bounded case, the one with the ellipse, or we can have different trajectories like this, bounded between two radii, r1 and r2. And the last one is a closed circular orbit. Okay. So for the Kepler problem, we have three types of orbits: open orbits, bounded orbits, or circular orbits. And the same nature of orbits is applicable for any potential V of r, any attractive potential. Okay, I will say any attractive potential V of r, which goes to 0 slower than 1 by r square and goes to infinity slower than 1 by r square. What does it mean? I will explain. Please look at this 5 plots. This is actually a graph of L square by 2m r square minus k by r raised to n versus r. In the x-axis you have r, the y-axis you have L square by 2m r square minus k by r raised to n. And here I fixed L as 1 by 2, m as 1.25. So this term will always be 1 by 10 r square. And in the second term, k is 1. And for different values of n, you will get, for n equal to 1, the second term will be minus 1 by r. N equal to 1.1, second term will be 1 by r raised to 1.1, and so on. Okay. I took last the value of n as 3. So that last term becomes minus 1 by r raised to 3. So these 5 graphs are corresponding to these functions. And this is for n is equal to 0.8. This is for n equal to 1, 1.1, 1.2, and this green one is for n is equal to 3. What is the nature, the difference of nature of these graphs? You can see that this 1 by r square term will go to 0 as r tends to infinity. This 1 by r term will also go to 0 as r tends to infinity. But which one will go fast? 1 by r square will go fast to 0 as r tends to infinity. Okay. So that is the meaning of this statement. Goes to 0 slower than 1 by r square as r tends to infinity. Okay. So in this cases. In these 5 cases, this 1 by r will go to 0 slower than 1 by r square. 1 by r raised to 1.1 will go to 0 slower than 1 by r square. 1 by r raised to 1.2 will go to 0 slower than 1 by r square. 1 by r raised to 0.8 will go to 0 slower than 1 by r square. But 1 by r cube will go to 0 faster than 1 by r square. Okay, so the first 4 cases satisfies this condition, and in all those cases we got a minimum, and the description of orbits will be same as that of Kepler problem. Okay, so in order to understand what is the meaning of going to 0 slower than 1 by r square, I will explain with this graph. This violet one is 1 by r square graph, and this light green is 1 by r, minus 1 by r. You can see that this black line is 0 line, and as r tends to infinity, this violet tends to 0 line faster compared to this green one, light green one. And this red one is 1 by r raised to 1.2. In that case, it is again it is slower than compared to 1 by r square. It is approaching 0 slower than 1 by r square. Even if you take any power up to say 1 by r raised to 1.99, it will be going to 0 slower than 1 by r square. And for any potential like minus 1 by r raised to n with n less than 2, you will get a minimum in the effective potential graph, and the nature of orbits will be same as that of Kepler potential. But if your power is greater than 2, then it will not have any minimum, and the nature will be different. That we will discuss now. You consider this case, that is V of r is equal to minus k by r cube. So V effective will be L square by 2m r square minus k by r cube. So this is the plot. This light green is L square by 2m r square. This violet is minus k by r cube, and these plots are for L is equal to 1, m is equal to 1, k is equal to 1. So this is plot of 1 by 2 r square minus 1 by r cube. Okay, this yellow line is effective potential, and the effective potential has now a maximum instead of a minimum. In the case of Kepler potential, there was a minimum, but now you have a maximum. So what are the possible trajectories? You consider an energy like this, a negative energy, E less than 0, the red line, and you can see that beyond this value of r, this yellow line is above the red line. That is, V effective is greater than total energy, and that is not physically possible. So the only possible motions are below this distance. So the particle will move such that it can never go beyond a particular value of r. It will be always less than that value of r. This is force center. Particle will be somewhere here. It can never go beyond this r. There is an upper bound. There is no lower bound, but there is an upper bound for this value of energy. Now consider this value of energy, this green one, and you can say that between two values of r, this yellow line is greater than this green one. So energy is less than V effective, or V effective is greater than total energy, and these regions are physically not possible. Particle can either can be in this region, or it can be in this region. Depending on the initial value, particle will be we can have two cases. Consider two circles, one with the radius r1, the other with the radius r2. If particle is initially beyond r2, it will always stay there. It can never come inside. If the particle is initially below r1, it will always stay there. It can never go to this region. So this region between r1 and r2 is forbidden. particle can either stay here beyond R2 or it can be below R1. Okay, these are the allowed regions, because here you have total energy is above V effective, and in this region also total energy is above V effective. This region between R1 and R2 is forbidden. Okay, so the nature of orbits is entirely different compared to the Kepler potential. Now consider another case, harmonic oscillator potential. V of r is equal to half k r square. Effective potential is L square by 2m r square plus half k r square. L square by 2m r square plus half k r square. So half k r square is this line. L square by 2m r square is this line. The sum is given by this orange line. Sum is given by this orange line. And if you consider any energy value above this green one, for this green one, the only possible trajectory is circle, because this R value is possible, energy is equal to V effective minimum, but beyond this R value, V effective is greater than total energy. Below this R value also, V effective is greater than total energy, and they are not physically possible. So the particle can move in a circular orbit. For any higher energy value, the motion will have two bounds. There is an lower bound, there is an upper bound. Okay, particle can never go beyond this value, beyond this R value, and below this R value. So motion will have two bounds, and energy values below this green are not physically possible. For any positive energy above this green line, the orbits will be bounded. Okay, you can explain this like that. Okay, now from the effective potential graph, we can obtain an value for the radial kinetic energy like this. You have the effective potential graph, this yellow one in the case of Kepler potential, and if the total energy is this black line, then this is total energy, this is V effective, and we know that E minus V effective is half mr dot square. So at any value of r, if you take the difference between these two, you will get the radial kinetic energy. If you are also plot the potential minus k by r, then the difference between E and minus k by r, that is total energy and potential energy, that difference will give you the kinetic energy, total kinetic energy of the particle. This is actually radial kinetic energy. Okay, the difference between effective potential and total energy will give you radial kinetic energy. Difference between total energy and potential energy of the particle will give you kinetic energy of the system, kinetic energy of the particle. Okay, so these are the information that we can obtain from the plot of effective potential. So I hope it is clear. Thank you.